Hi folks, welcome to 9.2. So let's hope for no random power outages to stop this lesson, but let's just kind of review a little bit about where we were at before I pick up where we left off, okay? So where we started yesterday was we talked about sort of situations that require more than two variables. But situations that, even though they have three variables, can still be modeled by linear equations. And so I had put you in breakout rooms to talk about these two examples here, just to kind of play around, see what comes up. And so I have the answers posted here in case you want to check your work. After that, and I think I actually forgot to record this part, so it's probably good that we go over this again. But after that, we talked about the three types of solutions, okay? And so when we're looking at a system of three equations with three variables in the linear systems, we can have what right here, the single solution, okay? And so the single solution is when you have three different planes and they cross at a single point. Now you'll know that you have a single solution when you work through the problem, and at the end you get x equals the number, y equals number, and z equals the number. And you'll write your answer as the x number, the y number, and then the z number, okay? Now, that's important. It's important to be able to go through the process of finding a single solution and using this as an opportunity to brush up on your algebra skills and your accuracy, okay? But what's also important is to sort of consider these other two cases. So in the second case, we have this infinite number of solutions. And that's a situation where you have the three planes and they all intersect, but they actually intersect at a single line rather than a single point. And so what we're going to see for our problems is, well, at the end, we might solve our equations and we end up with a true mathematical statement. Okay, so let me actually write that down over here. That at the end, we should have a true math statement, like 0 equals 0, or 3 equals 3, or negative 11 equals negative 11, but whatever it is should be true. It should make sense. And if you get 0 over equals 0, you don't panic. You're like, oh, okay. What I have here is a infinite number of solutions along a single line. And that's the line where all of the planes intersect, okay? Now I did plant a little seed for parametric equations that we're gonna take a look at in the next course in Math 104. We're going to take a look at parametric equations and how we sort of write them. And I want you to remember this, and I'll bring it up again, but I want us to remember this as one of the applications for parametric equations. Now, last but not least, we took a look at a case where there were no solutions, okay? Meaning that all three planes, the orange one, the blue one, the green one, they never meet at the same point or at the same line. It might be like two of them happening at the same time, or it could even be like part C, where all the planes are parallel and therefore they never touch, they never intersect. We don't get a solution from that. Okay. Now, what's the difference between the infinite number and the no solutions? Well, for the infinite number of solutions, we're going to get a true math statement at the end. But for the no solutions, we end up with a statement that is not true. 0 equals 3, or 5 equals negative 1/2, or 2 equals negative 2. Something weird that you're like, I know this is not true. Well, if it's not true, it means that there's no solution for that particular system, okay? And so as we went ahead yesterday, we used the idea that there are three types of solutions. And we took a look at one particular problem. And so our first example, we had a chance to look at maybe sort of the way that I think about them, but as you explore solving these systems on your own, you're going to find a way that works for you. Okay. And I encourage you to talk about that with your peers and with me or Val, because I think the more ideas you have on how to approach things, the more you're developing that toolkit of like, here's a random problem. How do I solve it? Okay. And so when we got to the end of example number 1, we realized that we found a number for x, y, and z. And so maybe we can even summarize this, that this solution has this system has a single solution. And what that means is all 3 planes, or like all 3 sheets of paper, intersect at the point 1, -1, 2, all right? And I just got those from my x, y, and z values. So x is 1, so the first number we put in is 1. Y is -1, so the second number we put in is -1. And then z equals 2, or the third number in our solution is 2, okay? So this is a good example of what happens when we work through the question and we're able to find numbers at the end, okay? So again, that means you've got 3 planes, they all intersect at a single point, and that point is 1, -1, 2. All right, so now let's take a look at example 2, and let's see what happens, okay? So for example 2, there's a lot of ways that we can sort of approach these problems. Remember, I said that I'm very biased towards elimination because I find that it works faster for me. But that might not be the case for you. So let's just go through this when using elimination. But if you have other methods, you're welcome to run them by me or run them by your peers or by Val, just to kind of like see, like, is this okay, right? So I'm going to start with these first 2 equations. And the reason why I'm going to start with those, and let's put a number 1 here, I'm going to start with these 2 because I have x and -x means I can just add my 2 equations together and get rid of one variable, get rid of the x. So let's write them out here. X minus 3y plus z equals 4. -x plus 2y minus 5z equals 3. And we'll add. Okay. So when we add, we're going to get, the x's go away, we'll get -y and minus 4z equals 7. Okay. So now based on that, I've gotten rid of the x's. I want to pick another pair of equations and get rid of the x's as well. And so I look here and I'm like, oh, check out these 2 equations down here. Well, I can say I have a -x and a 5x. So if I multiply the equation with the -x by 5, well, guess what? Then I have a situation where the 5x and the -5x cancel out. So we're going to times by 5, and that will give us -5x plus 10y minus 25z equals 15. And then I take the third equation, 5x minus 13y plus 13z equals 8. All right, let's add. Okay, negative 5x and 5x, the 5x's go away. That's excellent. I'm left with minus 3y minus, let's see, negative 25 plus 13 is negative 12z. And then 15 plus 8 gives us 23. Okay. So this was our second step, right? First step was to choose any two equations, get rid of one variable. The second step was choose any other two equations and get rid of the same variable. That way we can take this equation and figure out how to get rid of one of those letters, okay? So I noticed that I have a negative 3y, and this is a negative y. So I'm actually going to multiply this equation, so times by a negative 3, okay? And so what does that give me? Well, I get 3y plus 12z equals negative 21. Then I'm going to take the other equation, and when I add them, I should be able to get rid of the y's. Okay, so 0 plus 0 equals 2, or 0 equals 2. Okay, well, let's think about this for a moment. What does that mean? What does it mean when we have 0 equals 2? And essentially, we're saying, is this statement true or is it false? And check this out. This is false. We know that 0 doesn't equal 2, right? We know 0 doesn't equal 2. So what does it mean that we get a false mathematical statement at the end? Well, it means that there is no solution for this system of equations, okay? And what does that mean visually? It means there is no point or line where all three planes intersect, okay? So there's no solution. That's important to know. But beyond that, we want to know, is there an intersection point for all three of them? And the answer is no. There's no point or no line where all three planes exist. Okay. Let me just put that back on one screen for you. Give you a moment to pause here if you need to, and then we're going to move on to example number 3. All right, so another system of equations. 3 variables, 3 equations. All right, I know I've been using the first 2 together, but you can do that or you can do any combination of these. So just to kind of mix things up a little bit, I'm going to take the first one and the last one. And I notice I have 2x and x. So what am I going to do to this bottom equation? Well, I'm going to take this one and do times -2. That's going to allow me to cancel out the x's. So the first equation is 2x plus y minus 3z equals 0. And then the second one is going to be -2x plus 2y minus 2z equals 0. Got to be careful with your signs here, right? So I'm multiplying by -2. Let me make sure I did that correctly. -2 times x is -2x. -2 times -y is a positive 2y, and -2 times z is -2z. Great. Okay. So I end up with 3y minus 5z equals 0. Okay. All right. Well, let me take a look at maybe the second equation and the third equation. Okay. Now remember, I can choose any other pair I want to, but I'm going to choose one where I know I'm going to be like I kind of already know what number I'm going to multiply by. Okay. So let's see what we have here. We have a 4x and an x. So what should I do to the equation with the x to make it eliminate the 4x? Well, I'm going to times by -4. Okay, so 4x plus 2y minus 6z equals 0. Now let's multiply the bottom equation by -4. -4x plus 4y minus 4z equals 0. All right. 6y minus 10z equals 0. Okay. Now, let's go back and put in these steps, right? So I did this first, and then I did this part. And now that we have two equations with two variables, let's combine them. So this one and this one, I'm going to try and eliminate one of the letters. So let me try and get rid of the y's. I'm going to time the this equation by -2. Okay, so that will give me -6y plus 10z equals 0. And then I'm going to bring the other equation and plop it right underneath. 6y minus 10z equals 0. Oh, this looks kind of interesting. Well, on the left-hand side, I have 0. On the right-hand side, I have 0. So yeah, I didn't get a number out, right? So I know that these three planes do not cross at a single point. But is this true or false? 0 equals 0 is true, right? We know that 0 equals 0. But more importantly, what does that tell us about this system of equations? Well, this system has infinite solutions. All right, it has infinite solutions along the line that all three planes intersect at. Okay, so this system has infinite solutions along the line that all three planes intersect at. Okay. All right. So let's get both of those on one screen so we can see that in one case we had 0 equals 2, which was false. So we said there's no solution. But in the second case, we had 0 equals 0, and that's true. So that meant an infinite number of solutions along that line. Okay. All right, let's take a look at examples 4, 5, and 6. Okay. So let's see. Oh, this one looks a little bit different. I don't have an x in the second equation. That's actually kind of nice. That means they've done a little bit work for us. So if we are clever, we can take the first equation and the third equation where we have 2x and x. And if we want to add them together to get rid of the x, we're going to times by -2. Times that first equation by -2. That will give us -2x minus 2y minus 2z equals 2 times -2 is -4. And if I stack that on top of the third equation, 2x plus y plus 5z equals 0, let's see what we get. 0x negative y plus 3z equals negative 4. Excellent. All right, so I've actually got two equations that have the two of the same letters. This equation, the y minus 3z equals 1, and this equation, negative y plus 3z equals negative 4. And it looks to me like I can just add at this point, right? So let's write them on top of each other. Y minus 3z equals 1. Negative y minus 3z equals negative 4. 0 equals negative 3. Well, the question we ask ourselves is true or false? 0 equals negative 3? I think not. This is false. And it means that we have no solution. And we want to think in our brains, that means that all three planes do not cross at the same point or the same line. Okay? All right, let's move on to example 5. Give you a moment to look over those three equations. Here's what my long-term strategy is going to be. I'm going to take the bottom equation. I'm going to multiply that by negative 2 to pair it with the first equation. And then I'm going to take the bottom equation and I'm going to get rid of the x by doing negative 3. Okay? That's one way I could do it. Now, we've been getting rid of the x's pretty regularly. So for this example, I just want to show you we can get rid of any other letter first, and it's going to be the same. So just for kicks, let's get rid of the y's first, okay? So if I pair these top two equations, I have y and negative 3y. That means I'm going to times the y equation by 3, and then I can add. So I'm going to get 6x plus 3y minus 2 times everything by 3 times 3y minus 6z equals negative 3. And then my bottom equation is 3x minus 3y minus z equals 5. Okay, we have 9x minus 7z equals 2. Okay, so if I'm going to get rid of y in this equation, then what other pairs I pick should also get rid of y's. So I'm going to take the first equation and I'm going to pair it with the last equation. And this has y and negative 2y. So I'm going to take the y equation and times by 2. Okay? So that's going to give me 4x plus 2y minus 4z equals negative 2. And then my bottom equation is x minus 2y plus 3z equals 6. And I'm going to add them, and that should get rid of the y. 5x minus z equals 4. Okay, so we've just chosen a different letter to show ourselves that we can get rid of any letter we want to. It doesn't always have to be the x. So I'm going to take these two equations and think about the easiest way to eliminate a variable. And I'm going to do times this left-hand equation by negative 7. That's going to give me negative 35x plus 7z equals negative 28. And let's stack that on top of the other one. 9x minus 7z equals 2. And let's see what we get. Negative 35 plus 9 is negative 26x, and negative 28 plus 2 is negative 26. That means x equals 1, okay? Now, if you find a number, you really want to pause, double check, make sure this number is correct. Because you're going to use your x to find your z and to find your y. So if your x is wrong, guess what's going to be true about your other letters, right? Wah, wah, that's kind of sad. So let's set our point of double check this answer first, okay? So make sure you double check this. But once you have that, remember, we want to choose the path of least resistance. What is the most efficient way that we can find other variables? And so I'm going to take this x equals 1. I'm going to plug it into here. I get 5x minus 5 times 1 minus z equals 4, or 1 equals z. Okay. Last but not least, I need to find y. So I'm actually going to choose the top equation that we have. So 2x plus y minus 2z equals negative 1. And I'm going to plug in my x and y. So 2 plus y minus 2 equals negative 1. We get y equals negative 1. Okay. So if we write our answer as a final coordinate, we want the x value, which is 1, the y value, which is negative 1, and the z value, which is 1. Okay. So let's go back and maybe number these with the purple so we can kind of remember how we did this. We did this first, we did this second, we did this third, and then this was 4, and then we did 5, and then we wrote our whole answer. Okay. So these are definitely lengthy problems. On the exam, we're going to try and really work with answers that should be nice answers. Okay, you might see a fraction like a half or something like that, but it's not going to be any crazy fractions going on here. Okay, let's keep it simple. Let's work on the process, and more than anything, I want us to focus on strategy. How do we think? Not just 1, not even 2, but 3 or 4 steps ahead. Okay. All right, so let's round this out with one last example. We've got example 6. All right. So let's see. Scan through all 3. I think I'm going to try and eliminate z this time. Okay, just because we did a bunch of examples with x, we did one with y, let's just show we could do the same thing with z. Okay, so I'm going to pair the first and the second equation together. I have a z and a negative z. Whoa. So I can just add them together. X plus y plus z equals 7. 3x minus 2y minus z equals 4. Well, that gives me 4x minus y equals 11. Okay. Now, let's see. If I pick the first and the third, and I want to get rid of z, I have to multiply the first one by negative 5. So I could do that. Or I could say, let me take the second one and the third one. Then I only have to multiply by 5 rather than negative 5. Okay, so it's really up to you sort of how much you want to do sort of the work around multiplying and what's easier for you in terms of signs. Doesn't really matter either way. So I'm going to say we have our negative z and our 5z. So we're going to times the negative z equation by 5. So 15x minus 10y minus 5z equals 20. Okay. And then we stack it on top of the other one. x plus 6y plus 5z equals 24. All right, 16x minus 4y equals 44. Okay. So we've done elimination here, we've done elimination here. Now is the time that we compare the two equations we got and think about what multiplier might work best here. So I'm going to go ahead and multiply the top equation, so times by -4. Okay, that gives me negative 16x plus 4y equals negative 44. Let me stack that on top of our left-hand side equation. 16x minus 4y equals 44. Oh shoot, I think I know what's going to happen here. 0 plus 0 equals 0. Oh, or 0 equals 0. Okay. So remember, it's always a good time to double check your answers. Did you get all the signs right? Did you distribute everything you needed to? But after you've done that, if you get a true mathematical statement, here's what that means. That means there's an infinite number of solutions along the line where all three planes intersect. Okay, so we have an infinite number of solutions along the line where all three planes intersect. Okay, let me just move this all up on one screen for you. But that, folks, is the end of 9.2. All right, so we're gonna kind of keep it simple, keep it to the basics. I know this is already a lot of algebra here, but we really wanna think about, okay, what is our strategy and how do we do things in an efficient way, okay? All right, folks, I will see you in class tomorrow. Have a wonderful day and I'll talk to you soon. Bye.